For millennia, we humans have looked up at the stars and wondered about our place in the universe. We've sought answers to the biggest, most fundamental questions. Where did we come from? Are we alone? What is the nature of reality itself? But some of the most profound mysteries aren't out there in the vastness of space. They're hidden within the very fabric of our understanding, in the language of the cosmos itself, mathematics. Today, we're diving deep into the enigmas that have puzzled mathematicians for generations. These aren't just equations on a blackboard. They're gateways to new realms of understanding, bold challenges waiting for courageous minds to unravel them. Buckle up, because we're about to embark on a thrilling journey to the very frontiers of human knowledge. Get ready to explore the top 10 unsolved math problems that continue to tantalize and inspire. Problems so profound that their solutions could reshape our understanding of the universe and unlock secrets we can only begin to imagine. Imagine the universe of numbers, stretching out infinitely in all directions. Within this vast expanse, prime numbers exist, those indivisible building blocks of all other numbers. Now picture this. Mathematicians believe there are infinitely many pairs of these prime numbers that are only two numbers apart, like celestial twins dotting the cosmic landscape. 11 and 13, 17 and 19, 29 and 31, and so on. This is the essence of the twin prime conjecture, a tantalizing whisper from the universe that has captivated mathematicians for centuries. They see the pattern, they feel its truth deep down, but proving it, pinning it down with the rigor of mathematics, that's where the real challenge lies. This conjecture, proposed by the mathematician Christian Goldbach in the 18th century, is deceptively simple to state, yet maddeningly difficult to prove. It posits that every even number greater than 2 can be written as the sum of two prime numbers. Take the number 10, for example. It's the sum of 3 and 7, both prime, or consider 24, which can be expressed as 11 plus 13, again, both prime. Mathematicians have tested this conjecture to astronomical numbers, and it holds true, but a rigorous proof, a way to demonstrate its validity for every even number, remains elusive. This conjecture feels almost like a mathematical magic trick, a numerical puzzle with a simple set of rules that leads to an unexpected outcome. Take any positive integer, any number you like. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Now, with the result you get, repeat the process. Again and again and again. Here's the strange part. No matter what number you start with, you'll always eventually end up at 1. Try it yourself. Pick any number and see. It works every time, but the question is, why? Why this inevitable descent into the number 1? It's a question that has confounded mathematicians for decades, a numerical whirlpool we can't seem to explain. Chapter 4, the Riemann Hypothesis. This conjecture takes us to the heart of prime numbers, those fundamental building blocks of the number system. Proposed by Bernhard Riemann in 1859, it delves into the distribution of these primes, their seemingly random yet tantalizingly patterned occurrence along the number line. At the heart of the Riemann hypothesis lies the Riemann zeta function, a complex mathematical function that, at first glance, might seem far removed from the elegance of prime numbers. However, Riemann saw a profound connection. He hypothesized that all the non-trivial zeros of this function lie on a specific vertical line on the complex plane. If proven true, his hypothesis would unlock profound secrets about the distribution of prime numbers and revolutionize our understanding of number theory. Chapter 5. The Navier-Stokes Equations. These equations are the mathematical bedrock of fluid dynamics, describing how fluids flow, how air moves over an airplane's wing, how water swirls in a river, even the turbulent motion of stars in a galaxy. These equations are fundamental to our understanding of the physical world, yet their solutions in 3 dimensions remain elusive, locked away in a mathematical vault. Imagine trying to predict the exact motion of every molecule of water in a raging ocean, or the turbulent air currents within a hurricane. That's the level of complexity we're dealing with. The Navier-Stokes equations hold the key to unlocking these secrets, but their solutions remain one of the greatest challenges in mathematics and physics. Chapter 6. The P versus NP problem. This problem resides in the realm of computer science and computational complexity, but its implications extend far beyond. Imagine you're searching for a specific grain of sand on a vast beach. That's a difficult task, right? But what if someone handed you a sieve that magically filtered out every other grain of sand except the one you're looking for? Suddenly, the problem becomes much easier. That's the essence of the P versus NP problem. It asks, are there problems for which verifying a solution is easy, like checking if the grain of sand you found is the right one, but finding that solution in the first place is incredibly difficult, like searching the entire beach? Or are these seemingly intractable problems just waiting for the right algorithm, the mathematical equivalent of that magical sieve? This question has profound implications for everything from cryptography to artificial intelligence, and it's one of the biggest unsolved mysteries in computer science. Chapter 7. The Birch and Swinnerton-Dyer Conjecture. This conjecture takes us deep into the realm of elliptic curves, a type of mathematical function that has captivated mathematicians for centuries. Imagine a curve, smooth and flowing, described by a specific equation. Now imagine trying to find all the points on that curve where both the x and y coordinates are rational numbers, fractions that can be expressed as a ratio of two integers. The Birch and Swinnerton-Dyer conjecture proposes a profound connection between the number of these rational points on an elliptic curve and a special function called the L function, a kind of mathematical passport that encodes information about the curve. If proven true, this conjecture would have far-reaching implications for our understanding of number theory and the behavior of these intriguing mathematical objects. Chapter 8. The Hodge Conjecture. This conjecture resides in the abstract world of algebraic geometry, where shapes and spaces are defined by equations rather than drawn on paper. Imagine trying to understand the shape of a complex, multidimensional object by studying its shadows projected onto lower dimensions. That's a bit like what the Hodge conjecture attempts to do. It proposes that certain geometric shapes, called projective algebraic varieties, can be understood by studying simpler geometric objects called Hodge cycles. These cycles are like mathematical probes, revealing the hidden structure of these complex shapes. If proven true, the Hodge conjecture would provide a powerful tool for understanding the geometry of higher dimensions and unlock new insights into the nature of algebraic varieties. Chapter 9. The Yang-Mills Existence and Mass Gap. This problem plunges us into the heart of quantum field theory, the mathematical framework that describes the fundamental forces of nature. Imagine a universe governed by intricate fields that permeate all of space and time, fields that give rise to the particles and forces we observe. The Yang-Mills existence and mass gap problem challenges us to prove the existence of a specific type of quantum field theory, one that possesses a mass gap, meaning that the particles it describes have a minimum mass. This property is crucial for explaining why forces like the strong force, which binds quarks together inside atomic nuclei, have a limited range. Solving this problem would be a major triumph for theoretical physics, solidifying our understanding of the quantum world. Chapter 10. Beal Conjecture. This deceptively simple-sounding conjecture has puzzled mathematicians for decades. It revolves around an equation that looks almost like a more complex version of the Pythagorean theorem, a circumflex x plus b circumflex y equals sine c circumflex z, where a, b, c, x, y, and z are all positive integers, and x, y, and z are all greater than 2. The Beal conjecture states that if such an equation has a solution, then a, b, and c must share a common prime factor. In other words, there's no way to find a solution where a, b, and c are completely independent of each other in terms of their prime factorization. Despite its apparent simplicity, the Beal conjecture has resisted all attempts at proof, making it a tantalizing target for number theorists. As we've journeyed through these 10 unsolved math mysteries, we've only scratched the surface of a vast and uncharted territory. Each problem is a beacon, a challenge to the limits of human ingenuity. But more than that, they are reminders that the universe of mathematics is infinite, teeming with wonders yet to be discovered. Could you be the one to solve these? The next great math genius could be watching right now. The answers to these problems are out there, waiting for a curious mind, a flash of insight, a spark of genius to illuminate the path forward. Perhaps the key lies in a new branch of mathematics, yet to be imagined, or a fresh perspective on an old problem. What's certain is that the pursuit of these solutions will continue to drive innovation and expand the frontiers of human knowledge. The universe of mathematics is vast, and we've only just begun to explore its infinite possibilities. Subscribe for more mind-blowing math.